Okay, so hello everyone. In this video, I wanted to make an example of how we can compute the following points for the following circuit. Okay, we have here a voltage source of 120 and 0 degrees volts, RMS. Okay, and these are RMS voltage. Okay, and also we know that the frequency of this voltage source is 60 hertz. Okay, also we know that uh, we are connecting to this voltage source different loads in parallel. We have a load labeled as C1, in which we have a power. No, we know that this load is consuming an average power of 60 watts. Okay. No, this is not the average power. It is the reactive power. Sorry for that. No, we know that this load C1 is consuming reactive power. Okay, of 60 kilobar, and that the power, the complex power here has a power factor of zero equal to 0.85, and that the power factor is lagging. Okay. Also, we have another load labeled as C2, in which we have an average power of, or that we know that this load is consuming an average power of 90 kilowatts, that the reactive power of this load is 50 kilobars, and that the complex power is leading. Okay. And finally, we have their load, in which we know that the average power consumed by this load is 100 kilowatts, and that the power factor is equal to 1. Okay. So the idea is that we want to know what is the equivalent impedance of this circuit based on this information. Also, we need to compute the power factor of the parallel combination. Remember that here we have this voltage source that is providing power to each of the loads. Okay. So what we can do, okay, or we know that if we add the complex power of the first impedance, plus the complex power of the second impedance, plus the third power or the power related to the third impedance, if I add the values of these three elements, the complex power of these three elements, and I compute the angle of the equivalent complex power, I can know what is the power factor if I compute the cosine of the resultant angle. Okay. Also, we can see here that we need to compute the power factor of the parallel combination and finally determine the current supplied by the source. So we can also know what is the value of this current, okay? Because we know that the power that is distributed between each of the loads should be equal to the power of the voltage source, okay? No, the complex power of the voltage source. So that means that the power, okay, the complex power, no, let's label in this way. The complex power of the source should be equal to the complex power of load number 1 plus the complex power of load number 2 plus the complex power of load number 3. Okay? So the idea is that we can compute the complex power of the first load, the second load, and the third load. We can combine the three in order to obtain the complex power of the source. Okay? And based on that complex power, we can compute the power factor. Okay? And also we can use that complex power to find the value of the current of the circuit. Okay? That is provided by the source. Okay? So this is the approach. First, we need to compute the complex power of the first load, else L1, okay? We want to know what is this value. So based on the information that we have, we know that, well, we can conclude the following. First, we know that we have a reactive power of 60 kilowatt, okay? So we know that the reactive power is 60 kilowatt, okay? And more or less in this position should be the complex power, okay, SL1, or the complex power of load number 1. But we don't know the, the real power of load number 1. No, we don't know this real power, but we know the reactive power. And also we can know what is the angle, okay? Okay, the angle of this complex power, we can compute it because we know that the power factor is 0.85. And also, well, I can draw the complex power in the first quadrant because I know that the power factor is lagging. Okay? So since we have a lagging power factor, that means that the complex power is in the first quadrant of the complex plane. So based on this information, I can try to compute the real power. And with that real power or average power, okay, I can generate a representation for the complex power of the first load. So I need to compute the real power consumed by the first load. So this is equal to PL1 is equal, well, to find a relationship, I can use this angle and also a little bit of trigonometry, okay? So for example, we know that the tangent of theta L1, okay, should be equal to the opposite side, that is the reactive power, okay, divided by the adjacent side, that is the real power, okay? So I can solve this equation for this real power or average power, and I can conclude that this real power should be equal to 60 kilobar divided by the tangent, okay? The tangent of theta L1, okay? But theta L1, how can I compute it? Well, we know that the power factor is equal to the cosine of the angle of the complex power, okay? This is the angle of the complex power, that is this angle. So I know the power factor, that is 0.85. So if I solve this equation for the angle, I can get the following, that theta L1 is equal to the inverse cosine of 0.85, okay? So I can use this value and plug it into this relationship, okay? And well, I can express this as 60 kilobar divided by the tangent of the inverse cosine of 0.85. And this is equal to, just one moment, let me a second. The result of this operation to compute the average power should be equal to, just let me a moment, 96.814 kilowatts. Okay, so I have now the real power and the reactive power, okay, for the, and I can use this real power and reactive power in order to know what is the value of the complex power for the first load. So we have that the real power is 96.814. And also we have the reactive power, that is 60. J, no, this is the reactive power, that's why I am placing this imaginary number. And we are working with kilobars and kilowatts, so I can express this complex power as kilowatt ampere. Okay, so this is the complex power of the first load. Okay, and I can do the same to compute the complex power of the second load. So for the second load, okay, well, we have more information. For example, we know that we have the real power or the average power, that is 90 kilowatts, okay, plus, well, you can see here that they are telling us that the reactive power is leaving, okay? That means that this complex power for load number 2, okay, should be in this region, okay, should be in the fourth quadrant, because when you have a leaving complex power, that means that the complex power is in the in the fourth quadrant, okay? So we can conclude that the reactive power should be negative, okay? So we can place a negative sign to denote the reactive power, that is 50 kilobar. And So I can say that the complex power is 90 minus 50 kilovolt ampere. The reason I am considering here kilos, or kilovolt ampere is because I know that the real power is also expressed in kilowatts and the reactive power is also expressed in kilobars. Okay, so this is the second complex power. And for the third complex power, it is more easy because according to this information that we have, we can see that we only have a real power. We don't have reactive power because also the power factor is 1, okay? That means that we have a purely resistive element connected to, well, related to load number 3. Okay, so the complex power of load number 3 is basically 100 kilowatts. Okay, so remember that I defined this relationship, no? That basically states that the complex power of the source is basically adding these three values together. So we have the complex power of load number 3, the complex power of load number 2, and also we have the complex power of load number 1. Okay, so if we add these values together, we can obtain the equivalent complex power or the complex power provided by the source. That is equal to 286.814 plus 10J. Okay, 10J, and these are kilovolt ampere. Okay, so basically this is the result. Okay, what else? Well, I can also express this complex power of the source as in polar form. So this is equal to 186.988 with an angle of 1.99, 68 kilovolt ampere. Okay, so what else? Well, we now have the angle of the complex power of the source. Okay, so I can compute the power factor as follows. I know that the power factor of the circuit is equal to the cosine of this angle, that is 1.9968. Okay, so if you compute the cosine of this angle to compute the power factor of the source is equal to 0.99. Okay, so this is the power factor, and that is also the power factor of this parallel combination. Okay, and what else? Well, we can also use the following. We know the equivalent complex power. Okay, no, this is the complex power provided by the source. So with this information, I can also compute the current that is provided by the source, because remember that the complex power is basically equivalent to this. So we can say that the RMS phasor, no, the conjugate of the RMS phasor is equal to the complex power of the source divided by the RMS voltage phasor. Okay, and this is equal to 2.3915 with an angle of 1.99, 68 degrees kiloamperes RMS. Okay. Now, but this is the conjugate, no? This is the conjugate of the current, okay? But we can compute the conjugate or compute the actual value of the current by only changing the sign of the angle. No, so this is equal to, no, if I remove this conjugate, this is equal to 2.3915 with an angle of minus 1.99, 68 degrees amperes RMS. Okay, so this is the current, And what else we need to do? Well, we also can compute the equivalent impedance. Okay, so the equivalent impedance is basically the RMS voltage divided by the RMS current. So we know that this is equal to 120 with an angle of 0 degrees volts RMS divided by this current that is 2.3915 with an angle of minus 1.9968 degrees kiloamperes RMS. So the equivalent impedance, okay, of the circuit is 0.05414 plus 0.001748 J ohms. Okay, so this is like a tedious exercise, but I think that it combines many concepts together. Okay. Here also I wanted to notice that I am considering the kilo, this prefix, no, of the ampere for the ampere value, no, that are kilos, in order to compute the final value of the impedance. Okay. So that's all for this video. I hope you like it and see you later.